Video Lecture 2, Periodic Properties. Before we move on, let's check some of our concepts. Pause the video and answer the following questions. The modern periodic table is organized according to atomic number. The horizontal rows on the periodic table are called periods. And the scientist credited as the father of the periodic table is Mendeleev. When we read individual squares of elements on the periodic table, we get some pieces of information, like the name of the element and the symbol. From last unit, we remember that this number on top is the atomic number, which is equal to the number of protons in the nucleus. This number, as it exists right now, is the average mass, or the atomic mass. If we rounded this number, we would get the mass number of the most common isotope. This is the number of protons and the number of neutrons. This number down here we'll talk more about later. The periodic table also has groups and families and periods on it. When we talk about groups, we talk about vertical columns on the periodic table. So just like we see in these columns, these groups or families run up and down. Periods are horizontal, like we see these rowers in the boat. The reason that we refer to these is that the count for when to stroke is very important that all of the rowers stroke in time, that they're all working on the same period. There are also classes of elements based on the periodic table. We have the metals, which are on the left side of the periodic table. We have the nonmetals that are on the right side of the periodic table, and semimetals or metalloids, which are between the metals and the nonmetals. The two sides are actually touching the metals and the nonmetals. So where are the metals on the periodic table? On the left side, starting in period 2, and all the way down. Metals tend to be shiny, which we call lustrous. They're good conductors of heat and electricity. They're malleable, meaning that they can be hammered without shattering. They're ductile, which means that they can be drawn into wires, and except for mercury, are solid at room temperatures. Metals also tend to lose an electron to get a full octet in the valence shell. Elements tend to have less than 4 electrons in that valence shell. And we'll talk more about 2 and 3 a little bit later. Some different examples of metals are things like potassium. Potassium reacts with water and must be stored in kerosene. Copper is a relatively soft metal and a very good conductor of electricity, which is why copper is most often used in the wiring of houses and electronics. Mercury is the only metal that exists as a liquid at room temperature. Moving over from the metals are the metalloids. These metalloids are found on the staircase, the zigzag boundary line that exists between the metals and the nonmetals. Most often we would see a very dark line running down our periodic table. And our metalloids are the elements that are on either side of that solid line, except for, in group period 3, aluminum and silicon. Aluminum is a metal. Silicon is still a metalloid. And boron is also a metalloid. Metalloids tend to have 3 to 5 electrons on their outermost energy level, and they have properties of both metals and nonmetals. Our nonmetals are on the far right side of the periodic table, but it also includes hydrogen. Carbon is a great example of a nonmetal. Carbon is the graphite in pencil lead. It's a great example of a nonmetallic element. Nonmetals tend to be poor conductors of heat and electricity and tend to be brittle. They lack luster. Many are gases at room temperature. There's some solids. Bromine is the only liquid. They tend to gain electrons while forming ions, and these elements tend to have 5 or more electrons in their outermost energy level. Again, we'll talk about this gaining of electrons and the valence shell and the importance of that a little bit later. Some examples of nonmetals include sulfur. Sulfur is was once known as brimstone because of its very distinct smell. These spheres are actually microspheres of phosphorus, a very reactive nonmetal. And graphite isn't the only pure form of carbon. Diamond is also carbon. The color of different diamonds comes from impurities caught within the crystalline structure of those carbon molecules. So, before we go on, carbon is an example of a nonmetal. The vertical columns on the periodic table are groups. Remember, periods are the rows. The regions shaded below on the periodic table contain nonmetals. So let's look at some families of metals, nonmetals, and metalloids. The first, group 1A, the alkali metals. So this includes lithium, sodium, potassium, rubidium, cesium, and francium. This is group 1A, the alkali metals. These metals on the far left side of the periodic table, the alkali metals and the alkaline earth metals, are the most reactive metals. They're very shiny and soft, and they're very reactive, especially with water. Why are they so reactive? Well, let's look at their electron configurations. If we look, potassium with its 19 electrons has 1 electron all the way out here in its outermost energy level. Sodium with 11 electrons, again, is found all the way out here, is only that 1 single valence electron. It's these valence electrons that cause the alkali metals to be so reactive. Our second family is family in group 2A, the alkaline earth metals. This includes beryllium, magnesium, calcium, barium, strontium, and radium. These have a higher density and higher melting points than alkali metals, and they're also not as reactive. If we take a look at magnesium's valence shell, its outermost energy level, we see 2 electrons. This leads to our alkaline earth metals not being as reactive and a little bit higher density and higher melting point. The transition metals are in the D block. They're not very reactive, and therefore usually exist in their elemental state. Their main property is a resistance to corrosion. So when we look at our periodic table, this group here are our transition metals. These are the D blocks. If you notice, some of our precious metals like platinum and gold and silver are here. One of the properties of chromium is its color, and it's this silver-like color that's used to make jewelry. Our coinage metals, they're not very abundant. These are things like copper and silver and gold. Notice copper actually burns blue during a flame test. Our inner transition metals are the F block. These usually occur together and are very difficult to separate. These tend to usually lose 3 electrons and are of little commercial importance. These, in our F block, are our inner transition metals. Remember, they occur in this area here. Our P block includes group 3A, the boron family, group 4A, the carbon family, group 6A, or 5A, the nitrogen family, 6A, the oxygen family. Now, those 4 are all named for their first element. However, group 7A are the halogens. We have a special name for them. And group 8A, or group 18, the noble gases. We discussed the noble gases a little bit last unit. We used them a little bit last unit. The boron family, boron is actually the only semi-metal in the group. The rest of them are metals, like aluminum. Our carbon family has 2 semi-metals, Si and Ge, and it also has 2 important metals, tin and lead. We see 50% of the Earth's carbon present in limestone, and we use silicon silicon is in glass and is in sand and used to make glass. Silicon was also used to make microprocessors in computers. Group 5A, nitrogen. 80% of the atmosphere is nitrogen. It's not very reactive and most often used in fertilizers. Our oxygen group, our oxygen family. Oxygen is the most abundant element on Earth. Sulfur, like we mentioned before, was once called brimstone and is that very distinct smell you smell whenever the oxygen family. Oxygen is the most abundant element on Earth. Sulfur is that very distinct odor you smell whenever you light a match. Our halogens, these are the ones all in 7A, these are our salt formers. A metal plus a halogen forms a salt. One of the most common ones is sodium chloride. And finally, our noble gases, the least reactive and the most stable of all of our elements. Argon is the most abundant noble gas. Hydrogen is in a family by itself. It has 1 valence electron, like we see here, 1 valence electron. And because it's only 1 proton, it is light enough to escape the pull of gravity. So hydrogen travels through outer space, and hydrogen is actually the most abundant element in the entire universe.